quiet archive record. Tonight, we pass into a world that asks nothing of you. No urgency, no weight, just the quiet unfolding of a story. In physics, the speed of light is not only a very large number, it is a limit built into how space and time behave. Light in a vacuum travels at about 300,000 kilometers per second, and in modern physics that value, written as c, shows up everywhere. It connects energy to mass. It sets how fast information can move. It shapes what it even means for two events to be at the same time. This episode is a tour of 10 approaches people have proposed for reaching the speed of light, or appearing to, with a focus on what the ideas require, what blocks them, and what might be possible in the far future. Tonight, we go through 10 ways to reach the speed of light, or faster. To talk about reaching light speed, it helps to start with what the limit actually is. In everyday life, speeds add like simple numbers. If you run forward in a train that is already moving, the ground speed looks like train speed, plus your running speed. But as speeds approach c, the way velocities combine changes. In special relativity, the speed of light is the same for all observers who are not accelerating, no matter how fast they move. That is not a trick of measurement. It is built into the structure of space-time. The consequences are strange, but they are also measured. Moving clocks run slow compared to stationary clocks, an effect called time dilation. Moving lengths shrink along the direction of motion, an effect called length contraction. And as you push an object with mass faster and faster, its energy rises without bound. You can keep adding energy, but you get less and less extra speed. For any object with rest mass, reaching c would require infinite energy. That statement is not a guess. It is a direct result of the relativistic energy equation. That is why most serious proposals are not really about hitting exactly c with a normal spaceship. Instead, they aim at fractions of c, like 10%, 50%, or 99%. At those speeds, travel between stars stops being an endless story. The nearest star system is a little over 4 light years away. At 1/10 of c, it is a trip of decades. At half of c, it is a trip of under a decade, not counting acceleration and braking. At 90% of c, the trip is only a few years in the rest frame of Earth, and for the travelers, due to time dilation, it can feel even shorter. But relativity does not hand out free miracles. High speed does not only change time, it changes danger. At large fractions of c, even a grain of dust can hit like an explosive. Interstellar space is not empty. It is thin, but not empty. There is also the problem of braking. Getting up to speed is hard. Coming back down from it is also hard. Many concepts that look simple when they only talk about acceleration become complicated when they face the need to slow down at the destination. With that baseline, the first way to get to the speed of light is also the simplest. It is the method we already use. The first way is chemical rockets pushed to their limit, and then far beyond anything we can build now. A chemical rocket works by throwing mass backward at high speed. The forward push comes from conservation of momentum. Chemical reactions release energy from chemical bonds. That energy is real, but it is small compared to what is locked in atoms and nuclei. A typical chemical rocket exhaust speed is a few kilometers per second. The rocket equation tells you how hard it is to get high delta V when your exhaust speed is low. Every extra bit of speed demands a larger and larger ratio of fuel mass to final mass. People sometimes ask if you could simply stack stages. In theory, you can, and we do. But the equation does not care how many stages you use. You still need an enormous amount of propellant. The math gets brutal long before you reach a significant fraction of C. Even to reach 1% of C, which is about 3,000 kilometers per second, you would need an effective exhaust speed far beyond chemical energy. If you tried to do it chemically, the required mass ratio would be so huge it would not fit into any plausible engineering story. That does not mean chemical rockets are useless in a light-speed conversation. They are the baseline. They are the tool that gets you out of an atmosphere. They are part of a larger system. But as a direct path to light speed, chemistry runs out of energy. The second way is nuclear thermal propulsion. This is still a rocket throwing mass backward, but instead of heating the propellant with chemical fire, you heat it with a nuclear reactor. Nuclear fission releases millions of times more energy per unit mass than chemical reactions, not because it violates physics, but because nuclear binding energy is far larger than chemical bond energy. A nuclear thermal rocket typically uses a reactor to heat hydrogen and expel it through a nozzle. The advantage is exhaust speed. Hot hydrogen can reach higher exhaust velocity than chemical exhaust, which is limited by molecular weight and combustion temperature. Nuclear thermal designs can reach specific impulse, roughly double the best chemical engines. That is an enormous advantage for trips around the solar system. But for interstellar speeds, even doubling or tripling, the exhaust speed is not enough. The rocket equation still bites. To get to a significant fraction of C, you need exhaust speeds that are themselves a significant fraction of C, or you need a different method that does not carry all of its reaction mass. So nuclear thermal is a step up, but it is not close to C. It is still important because it leads into the next concept, where nuclear energy is used in a more extreme way. The third way is nuclear pulse propulsion, sometimes called an Orion-style drive. The basic idea is to ride a controlled series of nuclear explosions. Behind the spacecraft, you detonate small bombs. A pusher plate and shock absorbers transfer momentum to the craft. It sounds wild, but in terms of physics, it is direct. Explosions throw mass and energy backward. You ride the push. Orion-type concepts can, in theory, produce very high thrust and high effective exhaust velocity. They could move extremely heavy payloads. They could also, in theory, reach high speeds compared to other near-term ideas. But there are problems that are not only social and political, though those are real. The engineering is ugly. The pusher plate takes repeated hits. You need to manage neutron and gamma radiation. You need to carry a huge supply of pulse units. There is also a scaling problem. To get to a fraction of C, you would need enormous total energy. If you try to carry all of that in bombs, your ship becomes a moving nuclear arsenal. And then there is the interstellar medium. At high speed, every particle you hit turns into radiation. The front of the ship needs shielding. That shield becomes mass. Mass demands more pulse units. Orion is still interesting because it shows a theme. If you want to go fast, you need high energy density. Nuclear reactions have it. The next steps push nuclear energy further. The fourth way is nuclear fusion, rocket propulsion. Fusion is the process that powers stars. Light nuclei combine into heavier nuclei, releasing energy when the final nucleus has higher binding energy per nucleon than the initial ones. The The most famous fusion reaction is deuterium plus tritium, which releases a lot of energy, but also releases a neutron that is hard to direct. There are other reactions, like deuterium plus helium-3, that release more of their energy in charged particles that you can potentially steer with magnetic fields. A fusion rocket uses the fusion reaction products as exhaust. If you can direct the charged particles, you can get exhaust speeds that are far higher than chemical engines, potentially thousands of kilometers per second and beyond. In some concepts, the exhaust could be a significant fraction of C. The appeal is that fusion fuel is light. A gram of fusion fuel contains enormous energy compared to a gram of chemical fuel. In principle, you could accelerate a ship to perhaps 10% of C or more without carrying an absurd mass of propellant. In practice, the problems are severe. First, controlled fusion is still not a solved engineering problem, even for ground power. We have experimental devices that can approach or exceed brake, even under certain definitions. But a compact, reliable, lightweight fusion engine is far beyond current tech. Second, a fusion rocket needs to manage very hot plasmas and intense radiation. Third, it needs to reject waste heat. In space, the only way to dump heat is radiation. Radiators get large. If you imagine a starship with a fusion drive, a lot of its mass may be radiator, shielding, and structure, not only fuel. And at high speed, you have to handle impacts. Still, among serious interstellar concepts, fusion is one of the first that could plausibly reach a meaningful fraction of C. The fifth way is antimatter propulsion. Antimatter is matter with opposite charge and quantum numbers compared to normal matter. When antimatter meets matter, they annihilate, turning mass into energy. In the most direct form, matter-antimatter annihilation converts almost all rest mass into energy, unlike chemical or even fusion, where only a small fraction of mass turns into energy. If you could store antimatter safely and use it in an engine, the energy density would be extraordinary. The theoretical exhaust velocity could be extremely high, potentially approaching C. In some concepts, the annihilation products are used to heat propellant or to produce charged particles that can be directed. The obstacles are not subtle. Making antimatter is difficult. We can produce tiny amounts in particle accelerators, but it costs far more energy than you get back. That is not a violation. It is simply that our production methods are inefficient. Even if you had cheap energy, you would need industrial-scale antimatter factories. Then there is storage. Antimatter cannot touch normal matter. It must be held in electromagnetic traps, like penning traps, and kept extremely isolated. For neutral antimatter, like antihydrogen, storage is even harder. The more antimatter you store, the more catastrophic a containment failure becomes. Even if you solve those issues, you still have a problem common to all high-energy drives. The energy has to go somewhere. If you do not direct it into exhaust, it becomes heat and radiation. That heat must be managed. The radiation can damage electronics and crew. Antimatter remains one of the few concepts that, in pure energy terms, could in principle push a ship to very high fractions of C. It is also one of the least likely in the near future. So far, these first 5 methods share a pattern. They are rockets. They throw mass backward. They carry the energy source on board. That means the rocket equation is always present. The next ways change the pattern by moving the power source off the ship. or by changing what counts as reaction mass. The sixth way is a light sail pushed by a powerful beam, often imagined as a laser array. A sail is a large reflective surface. When photons hit it, they transfer momentum. Light has momentum, even though it has no rest mass. If you shine a beam on a sail, it pushes. The magic of the sail is that the ship does not carry propellant. The beam's source is elsewhere, perhaps in the solar system. That means the ship can be extremely light, and it does not need to accelerate fuel along with the payload. The limiting factor becomes the power of the beam and the mass of the sail and payload. This idea is not only science fiction. There are serious proposals, including concepts like Breakthrough Starshot, which imagines gram-scale probes pushed to a fraction of c by a huge laser array. In those proposals, the target speeds can be around 20% of c, but the engineering demands are huge. The beam must stay focused across long distances. The sail must survive intense light without melting. It must remain stable so it does not tumble. It must also handle the interstellar medium at high speed. There is also the braking problem again. A laser sail pushed from home can accelerate away, but how does it slow down at the destination? You could carry a second sail and use the light from the destination star, or you could use magnetic braking in the interstellar medium, or you could accept a flyby. Many early proposals accept a flyby. Still, beamed sails are one of the most realistic near-future routes to high fractions of CAE for very small payloads. For large crewed ships, the required beam power and sail size become extreme, but not obviously impossible in a far future civilization with huge energy resources. The seventh way is a particle beam pushed sail, often called a beamed core or beam-driven rocket. Instead of photons, you push the ship with a beam of particles, like ions. Particles carry momentum like photons, but for a given energy, massive particles can carry more momentum than photons. That can make the push more efficient in some regimes. In a particle beam concept, you have an accelerator somewhere, perhaps in orbit around the sun, that fires a stream of particles at a magnetic sail or some kind of collector on the ship. The ship uses the momentum exchange to accelerate. Like the laser sail, the ship does not carry the main energy source. The downside is beam spread. Particle beams diverge due to temperature, magnetic effects, and basic physics. Keeping the beam tight across vast distances is hard. There are also interactions with the interplanetary and interstellar medium. The beam can be deflected and can cause radiation. Still, particle beam propulsion is a serious idea because it changes the mass ratio story. If you can keep most of the heavy power infrastructure at home, the ship can be lighter. A beam-driven approach could, in theory, push payloads larger than the gram scale of laser sail proposals. The eighth way is an interstellar ramjet or related scoop drive. The idea, proposed by Robert Bussard, is to collect hydrogen from interstellar space as you travel and use it as fuel. In a classic Bussard ramjet, a huge magnetic field acts like a scoop. It gathers sparse interstellar hydrogen, compresses it, and feeds it into a fusion reactor. The ship then expels fusion products as exhaust. If you could do this, it would be a way to avoid carrying most of your fuel. In principle, you could accelerate for a very long time, approaching a high fraction of c. But there are serious doubts. The interstellar medium is thin. Even with a scoop thousands of kilometers wide, the mass you collect per second may be tiny. compressing the collected hydrogen costs energy. At high speed, the ship plows into the gas with enormous energy, which can become drag and radiation. The scoop itself may create more drag than thrust. There are variants, like the ramjet that uses the collected gas as reaction mass without fusing it, or a ram augmented drive. Some concepts use onboard power to accelerate collected mass backward, using space as a reaction mass supply. The ramjet idea is a perfect example of how interstellar travel forces you to think about the environment. Space looks empty, but at relativistic speeds, it is not forgiving. The same gas you hope to use as fuel becomes a hazard. The ninth way is a black hole drive. This is a category rather than one design. The idea is to use a black hole as an energy source or as a kind of engine. One concept is the artificial micro black hole. If you could create a tiny black hole of a certain mass, it would emit Hawking radiation. The smaller the black hole, the hotter it is, and the more power it emits. If you could feed mass into such a black hole and use the emitted radiation as a directed exhaust, you could, in theory, create an engine with extremely high energy density. A black hole is the ultimate mass to energy converter in a sense, because you can drop matter into it and get energy out as radiation. This sounds impossible, but it is interesting because it is constrained by physics rather than by chemistry. The challenge is that we have no idea how to create and control such a black hole. The energies required would be beyond any current accelerator. Even if you had one, you would need to keep it from evaporating too fast or from growing too large. You would also need to direct the radiation. Hawking radiation would include high-energy gamma rays and particles. Reflecting gamma rays is hard. You might need some kind of plasma mirror or a structure that uses pair production and magnetic fields to redirect the flow. That is deep, speculative engineering. But in a list of ways to reach light speed, black hole drives are included because they point to the far edge of what known physics allows. They also raise questions about how advanced a civilization might become if it can manipulate extreme objects. The 10th way is faster than light travel by changing the geometry of space-time itself, using ideas like warp drives and wormholes. Here, it is important to be precise. Special relativity forbids objects with mass from moving through space faster than light locally, but general relativity allows space-time itself to expand, contract, and curve. In cosmology, distant galaxies can recede from us faster than light due to the expansion of space, without violating local speed limits. A warp drive concept, like the Alcubierre metric, imagines a bubble of space-time where space is compressed in front of the ship and expanded behind it. The ship inside the bubble does not move faster than light locally, but the bubble can, in theory, move in a way that brings it to a distant point faster than a light beam traveling through normal space. Wormholes are another geometry idea. A wormhole would be a tunnel connecting two distant regions of space-time. If it existed and was stable, traveling through it could be faster than traveling through normal space. Not because you move faster, but because the path is shorter. The trouble is that these ideas appear to require exotic matter or negative energy density. In many analyses, the amount of negative energy needed is enormous. There are also problems with stability. Quantum effects may destroy a wormhole as soon as it is formed. Warp bubbles might create horizons that trap the ship. There are questions about how to control such structures without paradoxes. Still, these concepts are not pure fantasy. They are solutions to Einstein's equations under certain conditions. They show that the universe, in principle, has room for strange shortcuts. Whether those shortcuts can be made by engineering is unknown. That gives us the 10 ways at a headline level. But to actually understand what it would take, we need to slow down and walk through the details, because each approach has a different kind of difficulty. Some are limited by energy, some are limited by materials, some are limited by control, some are limited by the need to protect a ship from the space between stars. Start with energy. To accelerate a spacecraft to a fraction of c, you need kinetic energy. For a 1-ton craft at 10% of c, the kinetic energy is about 4.5 times 10 to the 17 joules, which is roughly the energy output of a major power plant running for years. For larger ships, the numbers rise fast. For half of c, relativistic effects matter, and the energy becomes a large fraction of the rest mass energy. Rest mass energy is given by E equals mc squared. 1 kilogram of mass is about 9 times 10 to the 16 joules. That number is why antimatter looks so tempting. In principle, annihilating a few kilograms of matter and antimatter could provide the energy to push a small ship to high speed. But then you need to capture and direct that energy into exhaust. Energy is not the only constraint. Power is also critical. Energy is total amount. Power is energy per unit time. To accelerate quickly, you need high power. If you accept a slow acceleration over years, you can use lower power. That trade changes design. For human travel, acceleration is tied to comfort and mission design. 1g acceleration feels like Earth gravity. It allows a ship to provide artificial gravity by thrust, but 1g for long periods quickly pushes you to high speed. At 1g, you reach 10% of c in about 35 days. You reach half of c in under 6 months. That seems fast, but it demands enormous energy and propellant. Most realistic interstellar designs accept lower accelerations, like a fraction of g or even much less. That makes travel time longer in the rest frame, but it reduces power demands. Now consider the rocket equation again. For a rocket carrying its propellant, the required mass ratio depends exponentially on delta V divided by exhaust velocity. Even with an exhaust velocity of 10,000 meters per second, which is excellent by chemical standards, getting to 1,000,000 meters per second is a disaster. With exhaust velocity of 1,000,000 meters per second, getting to 10 million meters per second becomes hard. That is why high exhaust velocity is the key for onboard rockets. Fusion and antimatter offer higher exhaust velocity, but they still have to carry propellant unless the drive is pure photon rocket, where you emit light backward. A photon rocket has exhaust velocity equal to c, which sounds perfect, but it has terrible thrust for a given power, because photons carry momentum but no rest mass. To get 1 Newton of thrust from photons, you need about 300 megawatts of power. That is enormous. For a meaningful ship, photon rockets require star-level power. There are hybrid ideas. One is to use antimatter to heat propellant, giving you high exhaust velocity without needing a pure photon rocket. Another is to use fusion products in a magnetic nozzle. Now consider beamed propulsion. Beamed sails move the energy source offboard. That means the ship does not carry a reactor or the fuel to run it. But it does not remove energy needs. It shifts them to infrastructure. A civilization that builds a multi-terawatt laser array is doing something huge. It is building power plants. It is building cooling systems. It is building optics and control systems on a vast scale. In that sense, beamed sail travel looks like a railway or a highway. The vehicle is light and simple, but the network is heavy. That is not a flaw. It is a different economic model. It might be exactly how early interstellar travel works. You build a huge pushing system at home, and you send small probes to nearby stars. If you want a crewed ship, you may need a pushing system that can keep pushing for a long time. Or you need an onboard power source. Or you accept a mission where the ship does not stop. It passes through the destination system and sends data back. The interstellar medium problem becomes serious above a few percent of C. Suppose a ship travels at 20% of C. In the ship frame, incoming hydrogen atoms are moving at 20% of C. Their kinetic energy is high enough to produce radiation when they strike the ship or are deflected. At 50% of C, the energy rises. At 90%, it is extreme. Even if the density of space is only a few atoms per cubic centimeter, the ship sweeps through a large volume each second. Those impacts accumulate. One proposed solution is a forward shield, perhaps made of thick material, perhaps combined with electromagnetic fields to deflect charged particles. But many interstellar particles are neutral, like hydrogen atoms or dust grains. A field does not deflect neutrals unless you ionize them. Ionizing them requires energy and equipment. Dust is especially dangerous. A dust grain with mass of a microgram at a fraction of C carries enormous kinetic energy. At 20% of C, it is like a high explosive. At higher speeds, it becomes like a small nuclear event. You can try to detect and vaporize dust ahead of the ship using lasers, or you can deploy a cloud of material ahead as a sacrificial shield, or you can build very thick shielding. Each method adds mass and complexity. Radiation is another problem. At high speed, the cosmic microwave background in the ship frame becomes blue shifted. At very high gamma factors, it can turn into high energy radiation. That means, at near light speed, the background radiation becomes dangerous. Then there is the issue of communication. If a ship goes near light speed, communication with Earth is delayed by light travel time, and relativistic effects shift frequencies. This is not a showstopper, but it changes mission design. These are reasons why many realistic interstellar concepts aim for maybe 10 to 20% of COA for early probes, perhaps higher for later missions, and reserve near light speed travel for very far future or for very small payloads. Now we can return to the 10 methods and expand each one with more detail, not in a numbered way, but as a continuous narrative. Chemical rockets, in their best form, are limited by the energy in chemical bonds. The best chemical propellants, like hydrogen and oxygen, release a certain amount of energy per kilogram. That energy sets the maximum exhaust velocity. You can optimize the nozzle and the mixture, but you cannot beat the thermodynamics. Even if you could build a perfect chemical rocket, the exhaust velocity would be at most on the order of 10 kilometers per second. When you use the rocket equation to reach even 1,000 kilometers per second, which is only about 1/3% of C, the required mass ratio becomes enormous. And that is for one leg. If you also need to decelerate, you need the mass ratio twice, or you need a staging strategy that essentially doubles complexity. That is why the fastest human-made objects are not chemical rockets by themselves, but combinations of chemical launch plus gravity assists and in some cases deep space propulsion. Probes like Voyager gained speed by passing planets and stealing a tiny bit of their orbital energy. That method is clever and cheap, but it is limited to the solar system and to trajectories that line up with planets. There are also solar sails using sunlight. Sunlight is a free beam. A solar sail can slowly accelerate a craft outward, but sunlight pressure is weak. It can push small craft, not heavy ships, unless the sail is enormous and very light. Nuclear thermal rockets improve exhaust velocity by using a reactor. This is more efficient than chemical, but the propellant still must be carried. If you want to reach high speed, you either need much higher reactor temperatures or different cycles. Gas core nuclear rockets propose using a fission reactor, where the fuel is in a gaseous form, allowing higher temperature. But then you face containment and radiation problems. There are even nuclear saltwater rockets, where fissile material dissolved in water goes critical as it exits the nozzle, producing a continuous nuclear detonation in the exhaust stream. The energy is enormous. The concept is terrifying. It would have exhaust velocities far above chemical, but it also would produce intense radiation. It could be a high-performance drive for interplanetary travel, but again, for relativistic speeds, it is still a rocket equation story. The nuclear pulse approach is a step change because it uses nuclear explosions. In space, there is no air to transmit blast, but the explosion produces hot plasma and radiation that can push a plate. The original Orion studies suggested that a ship could be built with relatively modest technology of the 20th century, in pure engineering terms, if not in political terms. The big advantage of Orion is not only high exhaust velocity, it is also high thrust. Many high exhaust velocity engines have low thrust and require long burns. Orion gives you both. That means you can accelerate a heavy ship quickly, but to get to very high speed, you need many bombs. If each pulse unit is like a small nuclear weapon, you are building a supply chain for tens of thousands of nuclear devices. Then you need a ship that can withstand repeated shocks. The pusher plate must survive ablation. Some designs include a layer of oil sprayed before each pulse to protect the plate. For interstellar travel, there is another issue. The exhaust plume of a nuclear pulse drive is not a nice, clean stream. It is a messy burst of plasma and radiation. Directing it for maximum efficiency is hard. Fusion propulsion is a major jump because it offers high energy density without needing actual bombs. There are many fusion rocket concepts. One is the inertial confinement fusion drive, where you fire pellets and compress them with lasers, causing micro-explosions. Another is the magnetic confinement fusion drive, where plasma is held in a magnetic field and expelled. Project Daedalus, a famous study from the 1970s, proposed an uncrewed probe powered by fusion. It would use electron beam-driven inertial confinement fusion of deuterium and helium-3. It aimed for about 12% of C. It would carry a huge mass of fuel, tens of thousands of tons, but it could in principle reach another star in decades. Later designs like Icarus revisited the idea with updated assumptions. The basic lesson was that fusion could do interstellar travel, but it demands an industrial-scale project. A crewed fusion ship would need life support, shielding, and likely a way to create gravity, either by rotation or by thrust. Long travel times raise issues of biology, psychology, and social structure. A mission lasting decades may require generations. Antimatter is the extreme. If you had enough antimatter, you could power a photon rocket or heat propellant to very high temperatures. But antimatter production is a bottleneck. In our current physics, antimatter is made by converting energy into particle pairs. That process is possible but inefficient. If you use a particle accelerator, you waste most energy as heat. A more advanced method might use intense lasers and fields to produce pairs more efficiently, but you still face the fundamental cost. To make antimatter, you need at least as much energy as the mass energy you want, and likely much more. Then you need storage. Penning traps can store charged particles, but the density is low. To store kilograms, you would need enormous volumes or new storage methods. You could imagine storing antimatter in the form of antiatoms in a neutral trap, or in a solid form. But that is beyond known methods. Even if you could store it, using it safely is hard. You would be carrying the equivalent of a large nuclear arsenal in energy terms. A containment failure would be catastrophic. Beamed laser sails take a different path. They rely on the fact that momentum can be transferred without carrying fuel. If you can build a gigawatt or terawatt laser array, you can push a very light sail to high speed over minutes or hours. For a gram-scale craft, acceleration can be enormous. You could reach 20% of c in minutes. That is a strange image. A tiny probe pushed by a beam becomes a relativistic projectile. But if you want to push a ton-scale craft, you need much more power, and the sail must be huge. The beam must be larger and more stable. The sail must survive the pressure and heating, and you need to keep the beam on the sail without losing lock. There are ways to improve. You can make the sail reflective at the laser wavelength. You can spin the sail for stability. You can use adaptive optics on the beam source. You can build the array in space to avoid the atmosphere. Each step is engineering heavy. Still, compared to building an antimatter factory, it might be easier. Now, consider particle beams. A particle beam pushing a magnetic sail has a different advantage. The sail could be a magnetic field rather than a physical sheet. That could reduce the need for a solid sail that might tear. A magnetic sail can be large without being a physical membrane, but a magnetic sail interacts with charged particles. The beam must be charged. The beam also spreads. There is also the issue of how to keep the beam collimated. In an accelerator, beams are kept tight with magnets. Once the beam leaves the accelerator, it can spread. One proposal is to use a series of beam stations that refocus the beam. That again implies infrastructure. Now, return to the ramjet concept, because it has a different flavor. A ramjet tries to use the hydrogen in space as fuel, but the density of interstellar hydrogen is low. In the local region near the Sun, it may be about 1 atom per cubic centimeter, though it varies. That is about 1 million atoms per cubic meter. That sounds like a lot, but an atom is tiny. The mass is extremely small. If you sweep a cross-section of 1 square kilometer at 20% of c, you process a large volume each second, but the mass collected may still be small. To collect enough mass to run a fusion engine, the scoop must be enormous. And then there is the issue of compressing and fusing the collected hydrogen. Hydrogen fusion requires high temperature and pressure. In a star, gravity provides pressure. In an engine, you need magnetic fields or inertial confinement. The collected hydrogen is mostly protons. You might need to carry catalysts like heavier nuclei to allow fusion cycles, or you might need to use proton-proton fusion, which is extremely slow. That makes a classic ramjet hard. A variant uses a fission reactor on board and uses collected hydrogen as reaction mass. That is a RAM augmented nuclear drive. It uses space as propellant rather than fuel. That reduces the need to carry propellant, but still requires onboard power. At high speeds, collecting the gas creates drag and radiation. The drag may be severe, so the ramjet might not be the first path to relativistic travel, but it remains an important concept. Now, black hole drives. The idea of hawking radiation comes from quantum effects near the event horizon. A black hole can emit particles and radiation as if it had a temperature. This leads to evaporation over time. For stellar mass black holes, the temperature is extremely low, and the evaporation time is longer than the age of the universe. But for tiny black holes, the temperature is high and the power output is high. If you could make a black hole of mass roughly 1 billion tons, it would have a power output that might be useful, but it would still be massive. If you make it smaller, the mass goes down and the power goes up, but the lifetime gets shorter. A starship black hole drive is therefore a balancing act. You want enough power to push the ship, but you want a long lifetime and you want a manageable mass. Then you need to keep the black hole in the ship, which means you need to hold it in place with forces. A black hole is mass. It responds to gravity, but gravity alone does not let you pin it. You might need to accelerate it with photon pressure or by feeding it mass in a controlled direction. All of this is deep speculation, but it is still physics-based speculation. Now, warp drives and wormholes. The Alcubierre metric is a solution to Einstein's field equations. It describes a region of space-time, a bubble, that moves. Inside the bubble, the ship is at rest relative to local space. The bubble moves because space contracts in front and expands behind. The problem is the stress-energy tensor needed to create this space-time. In many cases, it includes negative energy density. Negative energy is not common in classical physics. In quantum field theory, it can appear in small amounts and under constraints. It cannot be used freely without limits. There are quantum inequalities that restrict the magnitude and duration of negative energy. Some researchers have proposed modified warp metrics that reduce energy requirements, but the requirement for exotic matter often remains. Wormholes also have issues. A traversable wormhole would need to remain open. Classical solutions require exotic matter to hold it open against collapse. Even if you could make one, it might be unstable. It might collapse when matter enters. It might create radiation, so faster than light travel remains speculative. But the question includes or faster, so it belongs in the list. Now, another possible path to near light speed is not one of the 10 headline drives, but a combination. For example, you could use a fusion drive to leave the solar system, then a beamed sail to accelerate further, then a magnetic sail to brake. Or you could use a laser array to push a fusion-powered ship for a while, reducing onboard fuel needs. Many real design studies combine methods, but for this story, it is enough to keep the 10 as distinct families. Now consider what it would take to build the first human-made object to reach 10% of C. If you try to do it with a beamed sail probe, you need a sail mass of perhaps a few grams, a payload of grams, and a beam power of tens to hundreds of gigawatts for minutes. You need a laser array with large aperture, perhaps kilometers across, to keep the beam focused. You need to build it in space or on the ground with adaptive optics. You need to produce the power, perhaps by storing energy and releasing it quickly, like a giant capacitor bank. You need to aim the beam precisely. Then you need to communicate with the probe across light years. This is hard, but it is at least a clear engineering path. If you try to do it with fusion, you need a fusion engine that can run reliably for years, and you need a large fuel supply. You need a ship that can handle waste heat. You need shielding. You need a way to build and launch the ship. That is harder. So the first relativistic object is likely a small beamed sail probe. Now what about reaching the speed of light itself? For any object with mass, you cannot reach c, but you can approach it. In the limit, the energy required grows without bound. That means practical designs will pick a target speed, like 20%, 50%, or 90%. If you choose 90%, the energy per unit mass is already on the order of the rest mass energy, meaning a large fraction of mc squared. To get there, you likely need antimatter, or something like a photon rocket driven by a massive power source. But again, if the payload is small, it becomes less impossible. Now there is an important trick. Time dilation means that for the travelers, the galaxy can be crossed in a finite subjective time if you can maintain near light speed. But the energy cost is still huge. So if you imagine a far future civilization that can build a starship and supply it with energy comparable to a star, then near light speed travel becomes possible. But for our time, the realistic frontier is 10 to 20% of C for tiny probes. That is still profound. A probe at 20% of C reaches Alpha Centauri in about 20 years. It then sends back data. The data takes 4 more years to return. This would be a multi-decade project. Now, another issue that often comes up is propulsion efficiency. In an ideal rocket, you convert energy into kinetic energy of exhaust. The exhaust carries momentum. The ship gets equal and opposite momentum. The efficiency depends on exhaust velocity. If exhaust velocity is low, you waste energy accelerating exhaust you did not need. If exhaust velocity is high, you use propellant more efficiently. But if exhaust velocity is too high, you may waste energy if you do not need that high-speed exhaust. In interstellar travel, you usually want high exhaust velocity because delta V is large. So fusion and antimatter are good in that sense. Now return to the idea of a photon rocket. A photon rocket uses light as exhaust. Since light speed is c, it is the ultimate exhaust speed. That means in terms of propellant mass, it is efficient because you do not need to carry reaction mass. But in practice, you need to produce photons. That requires energy. If you use a reactor and convert energy to light, you have efficiency limits. If you use matter, antimatter, annihilation, you can produce photons directly. A pure photon rocket driven by antimatter could, in principle, reach very high speeds. But again, antimatter is hard. Now, beamed photon rockets could also exist. You could shine a beam on a ship and have it reflect or absorb and re-radiate. That is basically a sail again. Now, the story of reaching light speed is also the story of why light speed matters. Light speed sets the speed of causality in our universe. If you could break it, you could send signals to the past in some frames. That is why physicists are cautious. In general relativity, faster than light, travel through a warp bubble might still allow causality violations. Many researchers believe that some unknown physics prevents it, but we do not know. So for now, the safest view is that faster than light is not available, and near light speed is possible only with immense energy. Now, to keep this grounded, imagine building a probe that goes to 10% of C. At 10% of C, a dust grain is still dangerous. You need a forward shield. One idea is a thin layer of beryllium or other light material that can absorb impacts and be replaced. Another idea is a cloud of particles ahead of the probe, released gradually, that hits dust before the probe does. For a tiny probe, you could also accept losses and send many. Now, what about a crewed ship? A crewed ship needs shielding. It needs a habitat. If the trip is decades, it needs food production or stored food. It needs a stable society. Many concepts for crewed interstellar travel are generation ships. They are large and slow compared to relativistic probes. Another concept is suspended animation, but that is speculative biology. Another is to keep the travel time short by going fast, but that requires huge energy. So in the near term, human interstellar travel is not likely. But the question is not what is likely, it is what ways exist. So the 10 ways remain valid. Now, it is worth examining why C is so hard to reach. In Newtonian physics, kinetic energy is half mv squared. That suggests energy rises as v squared. But in relativity, kinetic energy is gamma minus 1 mc squared. Gamma is 1 over the square root of 1 minus v squared over c squared. As v approaches c, gamma goes to infinity. That is why energy goes to infinity. So any plan that tries to push a massive ship to C is impossible in that sense. But approaching C with a small object is possible. Now, if you are thinking about faster than light, you need to step out of special relativity and into general relativity. In general relativity, space-time can be curved and dynamic. It can expand. In an expanding universe, distant galaxies can recede faster than light because it is space that is expanding. So the idea of a warp drive is to create a controlled region of expansion and contraction. This is an idea, not an engineering plan, but it is included as the 10th way. Now, another faster than light idea is quantum entanglement. People sometimes think entanglement allows instant communication. It does not, according to standard quantum mechanics. Entanglement correlations are real, but they cannot be used to send information faster than light without additional assumptions. So it is not on the list. Now, another concept is tachyons, hypothetical particles that move faster than light. They have imaginary mass in the math. There is no evidence they exist. They also create causality problems. So they are not a practical method. The list stays with warp and wormholes as the serious faster than light category. Now take a step back and think about what the phrase "reach the speed of light" means for technology. It is a challenge because it demands control over energy at an extreme level. Even reaching 10% of C demands more energy than most human projects. So the story of light speed travel is really a story about energy production. It is also a story about materials. A ship at high speed needs strong, light materials. It needs radiation-hard electronics. It is a story about control systems. A beamed sail needs precision. It is a story about politics and economics. Building a laser array is a global project, and it is a story about patience. Interstellar missions take decades. Now, since this episode is framed as 10 ways, it is useful to hold each method up against a few questions. How much energy does it require? Where does the energy come from? Does it require carrying fuel? Can it brake at the destination? What payload can it carry? What are the main physics obstacles? And what are the main engineering obstacles? Chemical rockets have low energy density. Energy comes from chemistry on board. Fuel is carried. Braking is possible only with more fuel. Payload can be large within solar system. Obstacles are energy and mass ratio. Nuclear thermal has higher energy density, but still limited. Energy comes from fission on board. Fuel is carried. Braking possible with fuel. Payload can be large. Obstacles are reactor mass, radiation, heat. Nuclear pulse has high energy density. Energy comes from fission or fusion bombs on board. Fuel carried as bombs. Braking possible with bombs. Payload large. Obstacles are engineering of plate, radiation, political issues. Fusion has high energy density. Energy on board. Fuel carried. Braking possible with fuel. Payload can be large but ship mass huge. Obstacles are fusion control and heat. Antimatter has highest known energy density. Energy on board. Fuel carried. Braking possible. Payload could be large. Obstacles are production and storage. Laser sail has energy off board. No fuel carried. Braking hard. Payload small to medium depending on power. Obstacles are beam and materials. Particle beam is similar. Braking hard. Obstacles are beam spread and medium interaction. Ramjet uses energy on board, but fuel from medium. Braking possible by turning engine. Payload unknown. Obstacles are drag and fusion of collected fuel. Black hole drive uses extreme energy source on board. Fuel might be any mass fed into hole. Braking possible. Payload unknown. Obstacles are creating and controlling black hole and directing radiation. Warp and wormholes use geometry. Braking depends on control. Payload unknown. Obstacles are exotic energy and stability. That comparison shows why different methods live in different eras of possible technology. Now, imagine the near future, a few decades from now. We might build better chemical rockets, but they will not change the interstellar picture. We might build nuclear thermal rockets for Mars missions. We might build a small laser sail test in the solar system. We might build a fusion power plant, but not a fusion rocket. We will not build antimatter starships. So the first steps toward light speed travel will likely be about small probes and beamed propulsion. Now, imagine a farther future, centuries from now. A civilization might have cheap fusion. It might have large space industry. It might mine asteroids. It might build large structures in space. It might then build a laser array for interstellar probes. It might also build fusion-driven probes. It might begin to build beam stations. Now, imagine millennia from now. A civilization might harvest a significant fraction of its star's energy. It might then push larger ships with beams. It might build interstellar infrastructure. It might create antimatter in industrial quantities. It might attempt black hole engineering. It might discover new physics. But this is speculation. The point is that each method fits a different level of capability. Now, in a discussion of light speed, there is also a common misunderstanding about relativity. People sometimes think that because time dilates, you can cheat energy. You cannot. Time dilation helps the traveler experience less time, but the energy required to accelerate the ship in the rest frame remains. So a near light speed ship does not get a free ride. Another misunderstanding is that you could use gravity to reach light speed. Gravity can accelerate objects. But to reach near C, you would need to fall into a deep gravitational well, like near a black hole. You could, in principle, use a black hole as a slingshot. But to then keep the speed relative to your origin, you need to climb out, which costs energy. In general, gravity assists redistribute energy between objects. They do not create it. However, gravitational assists are still useful. In the solar system, you can use Jupiter and other planets to change trajectories. In a far future interstellar context, you could use stars as slingshots. But to get to high fractions of C, you still need a powerful drive. Now, there is one more important idea. In a relativistic regime, the difference between energy and mass blurs. Any energy you carry contributes to your mass energy. If you carry fuel, that fuel adds mass. If you carry a power source, it adds mass. Even the kinetic energy of your exhaust is part of the mass energy budget. So designing a relativistic ship is a closed-loop problem. This is why some researchers treat the problem in terms of energy per payload mass, rather than in terms of propellant. Beamed propulsion avoids some of this by keeping the energy source external. But then, you must build the external source. Now, to complete this episode as a continuous documentary, it helps to pick a concrete example and walk it through. Picture a tiny probe, perhaps a few grams. It has a sail a few meters across. It carries a small camera, a sensor package, and a communication laser. It is launched from Earth orbit or from a solar orbit. A huge laser array turns on for a few minutes. The beam hits the sail. The probe accelerates at thousands of G. Within minutes, it reaches 20% of C. The beam shuts off. The probe coasts for 20 years. As it approaches the target star, it has to take images quickly, because it will pass by fast. It sends data back with a laser. The data takes 4 years to return. This is a plausible, near-future interstellar mission. Now, picture a fusion probe like Daedalus. It is huge, thousands of tons. It is built in space. It carries fuel pellets. It ignites them in a pulsed fusion drive. It accelerates for a few years. It reaches about 10% of C. It coasts for decades. It then uses a second stage to slow, or it accepts a flyby. It sends data. This is also plausible in a far future, but it is a massive project. Now picture a crewed ship. It is enormous. It needs shielding. It needs life support. It may rotate to create artificial gravity. It may have a fusion drive. It accelerates slowly. It takes decades to reach another star. This is far future. Now picture an antimatter ship. It is a fusion of extreme physics and extreme engineering. It carries antimatter in traps. It uses it to produce energy. It accelerates a ship to high speed. This is even farther. Now picture a warp bubble. It is not even clear how to start, but it is included. Now, to keep the 10 ways clear, we can take a narrative pass that circles through each one again with added detail and keeps the tone factual. Chemical rockets are the first human method. They are limited by the speed of exhaust. The best chemical engines have specific impulse around 450 seconds. That corresponds to an exhaust velocity of about 4 to 5 kilometers per second. With staging, you can reach perhaps tens of kilometers per second relative to Earth. With gravity assists, you can reach tens of kilometers per second relative to the Sun. To reach 1% of C, you need about 3,000 kilometers per second. That is nearly 3 orders of magnitude higher. Chemistry cannot do it. Nuclear thermal rockets can reach exhaust velocities, perhaps 8 to 9 kilometers per second, maybe more with advanced designs. Still far from what you need. Nuclear pulse propulsion can reach effective exhaust velocities much higher, perhaps tens of kilometers per second or more. Still, to reach a few percent of C, you would need huge bomb supplies. It might do 1% or a few percent for a large ship. Fusion can reach exhaust velocities of thousands of kilometers per second. That makes 10% of C possible. It still demands huge fuel. Antimatter can, in principle, drive exhaust velocities approaching C. That makes high fractions of C possible. Laser sails can reach high speed if the payload is tiny. They might reach 20% of C. Particle beam propulsion could also reach similar speeds if beam control is solved. Ramjets could, in theory, reach high speed by using the medium, but likely face drag. Black hole drives could, in theory, offer extreme power. Warp and wormholes could, in theory, bypass the speed limit. Now, a careful listener might notice that some of these are not exactly ways to reach the speed of light. They are ways to approach it. That is the honest story. The speed of light is a hard limit for matter, but reaching a significant fraction of it is within known physics. So the question becomes, what fraction matters? For travel to nearby stars, 10 to 20% matters. For travel across the galaxy, near light speed matters. And for crossing billions of light years, faster than light would matter. So the 10 ways span scales. Now there is also a category of ideas that use gravity wells, like using a black hole as an engine by skimming its accretion disk or by using its rotational energy. A rotating black hole stores enormous energy in its spin. The Penrose process and Blandford's Znajek mechanism describe ways energy can be extracted. In astrophysics, jets from active galaxies show that black holes can power enormous outflows. A hypothetical advanced civilization could perhaps use a black hole as a power plant, and then use that power for propulsion. This is related to the black hole drive category. But again, it is far future. Now, another issue is efficiency of converting energy to thrust. A beamed sail is efficient in the sense that the ship does not need to convert energy on board, but the beam source must produce the energy. A fusion rocket must convert nuclear energy into directed exhaust. The conversion efficiency depends on plasma control. Antimatter conversion depends on capturing annihilation products. Black hole conversion depends on capturing radiation. Warp conversion is unknown. So in all cases, energy control is key. Now consider the human urge to push limits. We started with walking speed, then horses, then steam trains, then aircraft, then rockets. Each step required a new energy source and a new way to control it. Light speed travel is the next step, but the gap is large. It requires not only energy, but also patience and global scale coordination. Now, to close, it is useful to state a simple truth. The speed of light is not a wall in the usual sense. It is a rule about how space-time works. We can approach it, but we cannot cross it with normal matter. We can, in theory, bend space-time and create shortcuts, but we do not know if that is possible. So the most grounded path to reaching the speed of light, or faster, is actually two paths. One is to build engines and systems that can push small probes to high fractions of C. The other is to keep studying the deep structure of space-time and energy, because if faster than light is ever possible, it will come from new understanding. Until then, the 10 ways are a map of what we can imagine and what physics allows. They range from chemistry, which is familiar and limited, to fusion and antimatter, which are powerful and hard, to beams and sails, which demand infrastructure, to black holes and space-time geometry, which sit at the far boundary. And in that range, there is room for real progress, because even 10% of C is enough to turn the nearest stars from unreachable lights into destinations. This was a quiet archive story, where the story ends, sleep begins,